All right, guys, I'm gonna go ahead and start. I'd like to start by saying thank you all for coming. I'm assuming you're here for the undergraduate SIAM presentation. If not, then one of us is in the wrong place. Yeah, I'm Walter. I'm the president of the SIAM club here. And yeah, today we're going to be building a neural network from scratch. What do I mean from scratch? Well, there's a lot of very helpful libraries out on the internet, like Keras and TensorFlow and PyTorch and scikit-learn. But upon learning about neural networks and how to use these models, I didn't feel like I got a really good fundamental grasp of how do these things work under the hood. And so I think it's a really great exercise to build them from the ground up, just using math and NumPy. NumPy we're just going to use for our standard matrix operations and stuff like that. And yeah, I think you're going to come out on the other side knowing a lot more about neural networks. I know I did when I built this. So yeah, I'll assume that you guys have pretty good understanding of like multivariable calculus, linear algebra, stuff like that. I'm also going to assume that you're fairly familiar with fundamental coding concepts. So when I talk about like a for loop, I'll assume you know what that is. If you guys aren't super familiar with any of those concepts, I think that's fine. You can just learn by doing. I think it's all pretty straightforward, and you'll build some intuition as we go. Okay, I'll go ahead and start. So the first thing I'm going to do is a bunch of math. So I'm going to lay out like how do these things work, just in an abstract sense, like given our tools of calculus and linear algebra, and then we're going to convert that over to Python. Okay. So I'll start with our overall implementation design. So let's think about machine learning, the general steps, right? And bear with me, I just got one of these fancy new pens. So yeah, I'm a little slow on the whole tablet scene, but I'll do my best. Okay. Okay, so pretty universal steps for machine learning, right? We have some function that we're trying to approximate. So we've got an input and we've got an output, and we want to find the connection between the two. So we make some kind of assumption about the structure of our model. And then our first step is to throw data into that model and see what comes out the other side. So step one, data goes through the model. And then after we do that, we need some kind of objective function because we have a desired output, right? What we're trying to predict. And we need some way to measure, okay, how far away is our prediction from the actual observation. So we do this by defining some cost function. And there's a lot of different ways to do this, but the specific cost function we'll be using is called mean squared error, and I'll define that later. And then after we get the information about how far our prediction is from the actual desired output, we need some method for tweaking the parameters of our model. And this becomes an iterative process, and we repeat until we get a pretty good predictive model. So step three is to tweak our parameters. And then we repeat. So for our neural network design, we're going to be thinking of each layer as an individual function. And the reason we're going to be doing this is so that we can create modular code, and that's going to grant us a lot of flexibility in terms of when we define a new neural network, we'll be able to apply it to a variety of different tasks. So we can think of each layer as a standalone black box function. And like any function, it's going to have some input x and some output y, right? And this is going to describe our first step of our machine learning process, right? And then after we get our output, we're going to measure, right? What's the distance between our desired output and our prediction? And then we're going to pass that information backwards into our layer and use that to adjust our parameters. So we get our output y, and then on the way backwards, given our cost function c, we measure. Sorry, the handwriting is pretty bad. It'll get better as we go through. But we measure, right, how does the cost function change with respect to our output? And we have to pass that back into our layer, okay? And then these layers are in a sequential structure. So the output of one is the input for the next. So when we're going backwards, we also have to pass back what is the change in the cost function with respect to the input of this layer, because that's going to be the change of the cost function with respect to the output of the previous layer. So we are also going to pass back this derivative, partial c, with respect to the input. Right, and so with this design, we can think of each layer as its own individual object, and we can put them together in a sequence. And this defines our sequential model, right? This is our simple feed-forward neural network. So then if we have, say, 3 layers, we're going to pass in some input to layer 1, and we'll get out some output, and then that's going to be equal to the input of the next layer. Right, and then we go backwards. So we have some derivative here, and we pass that backwards. We get the derivative with respect to the input, and that's going to be the derivative with respect to the output of the previous layer. And that's how our model propagates, right? And then we just continue that process. Okay, so I've talked about layers, but what is actually going on inside of these layers, right? Well, essentially, they're functions. So one type of layer we're going to be talking about is the dense layer, and this is also referred to as a fully connected layer. So each of these nodes on the left indicate some instance of our input. So we can have x1, x2, x3, down to xi, right? And so we're going to pass in some I by 1 vector x. And on the other side, we're going to get some output y. And this is going to be y1, y2, down to y sub j. And now what are all these funky lines between the neurons? Well, those represent our weights. So here, every single y1 is a linear combination of all the x's from the previous layer. And so, for example, y1 is going to be equal to some weight times x1 plus some weight times x2. And so we can represent the weight corresponding to the jth output and the ith input as wji. And I'll just finish writing out this equation. And then we also include a bias term. And what this does is it allows us to shift our function to the left or right. Okay. So this lends itself pretty nicely to a matrix equation. So I'm going to grab this and move it over here. Oh, okay. That's fine. And I'm going to rewrite this as a matrix. So we can say that our output vector y is equal to our W matrix W, weight matrix W times our input vector X plus our bias vector. And what does this look like? It's going to be some y1, y2, yj is equal to W11 So that's going to be our weight matrix. Vector plus our bias vector. And just to check the shapes on all these to make sure that we're on the right track, right? This is a j by 1 vector. This is going to be a j by I matrix, an I by 1 vector, and a j by 1 vector. So that looks like it all checks out. Whoa. Okay. So that describes the forward propagation process for our dense layer. Now we need to figure out, okay, given our gradient information or given our derivatives, how do we tweak our parameters here, right? The parameters being these weights and biases. Okay. So for the back propagation, we're going to, given our cost function C, right, we want to minimize that to 0. So this is going to be called gradient descent, right? So we have this cost function, which is a function of, well, depending on the size of your neural network, thousands of variables. But our goal is to just reduce it to 0. Okay, so we're going to compute. We can compute directly the derivative of our cost function with respect to our output because, well, we just got our output out of the function, and the cost function is a direct function of the output y. But what we want is the information that tells us how to change our parameters, right? So this is, how does the cost function change when we tweak the weights? How does the cost function change when we tweak the biases? So we want partial C with respect to W, partial C with respect to B, And also remember in our sequential model, we needed to pass back the derivative with respect to the input because that's the derivative with respect to the output of the previous layer. So we also want partial C, partial X. Okay. So using the chain rule, let's start with this weight derivative, okay? So using the chain rule, we can say partial C, partial W is equal to the derivative with respect to Y times the derivative of Y with respect to W. Okay, and so let's look at a singular example. So for example, if I want to compute the derivative with respect to W12, so that's going to be this guy up here, then this is equal to the derivative with respect to Y1 times the derivative of Y1 with respect to W12 plus the derivative with respect to Y2, right? Because C is a function of Y1, Y2, Y3, all the way up to Y sub J. So let's look back at our equation up here. Actually, I'm going to grab this again. We're going to use this a lot. Move this down here. Okay, so for example, let's look at the derivative of Yj with respect to W12. Well, that's just 0. And actually, every single one of these terms is just equal to 0, right? Because W12 only shows up in this equation. So we only need to compute this term here. And hey, oh yeah, also we have pizza, so feel free to grab that. And if we look back at this, yeah, if we look back at this equation, right? So we're trying to find the derivative of Y1 with respect to W12. Well, that's just equal to X2. So we see that this is just equal to partial C, partial Y1, partial Y1. Nope. Got ahead of myself. Times X2. And in general, we see that the derivative of the cost function with respect to Wji is equal to the derivative with respect to Yj times X sub I. And so we get this matrix for the derivative with respect to W. But this is just the matrix multiplication, or rather the dot product, no, the outer product between partial C with respect to Y and our input vector transpose. And so that's going to describe how we find those derivatives of the weights. And I'll try to speed this up a little bit so we can get into some coding. So similarly, we want to find the derivative with respect to the biases. So if this vector is given by this, consider we just want to find partial C with respect to B1. Well, that's just equal to, hey, partial C, partial Y1, using the chain rule again, partial B1. Looking back at this equation, right, the only Y variable that depends on B1 is Y1. So all these go to 0. And what is the derivative of Y1 with respect to B1? That's just 1. So we get that the derivative of the cost function with respect to B1 is just the derivative of the cost function with respect to Y1. So partial C, partial B is just equal to the derivative with respect to Y. And then finally, we need the X, right? And so looking back at, you'll find this is a common theme for deriving these derivatives. We use the chain rule. Okay, so looking back at our equation for our output, right? The derivative of y1 with respect to x1 is just w11, and the derivative of y2 with respect to x1 is just w21, and so on. So we get that this is equal to partial C, partial, oops, yeah, wait, I'll do it like this, w11 and I think it's a lot more illuminating when you write it all out, but I'm going to try and speed through this a little bit. This gives us the matrix equation W transpose times the derivative with respect to Y. Okay, and so that describes our entire dense layer, right? So when we have some layer, now we have the given this derivative, we know how to change the parameters inside, and we know what the derivative is to pass back to the previous layer, so that layer can do the same thing. Okay. Now, there's another type of layer we use, and it's called the activation layer. So in the previous layer, I just described a dense layer in which we compute a linear combination of the input. But if we only computed linear combinations of the input on every single step, then our neural network just becomes a very fancy and a very expensive linear regression, right? And so that can't do anything very interesting for us. So we need to apply some nonlinear function at each step to our output. And so a lot of the times in neural network architecture, you'll see that these activation functions are applied directly to the output of the dense layer. But in our sequential model, the code just becomes a lot easier to write when you treat them as separate layers. You get the same result. And similarly, so here we don't have any weights and biases. We let the dense layer take care of that, but we do have this activation function. And so we need to take the derivatives with respect to that and use that information and see how that affects our cost function. Okay. And so the only derivative we're finding here is the derivative with respect to x. So given this, we just want this vector here, right? And again, let me rewrite something here real quick. And so we're just applying the activation function to each specific node. So a more accurate architecture would look like this, where each y is just a function of the corresponding x. Right, because all the x's already carry all the information that corresponds to the linear combination of the previous layer. Okay, so let's look at one of these variables. Derivative with respect to x1. This is just, again, chain rule. But if we keep having the derivative of y2 with respect to x1, y3 with respect to x1, well, these are all just functions of the corresponding variable, so those all go to 0. So we just get this here. And what is the derivative of y1 with respect to x1? Well, that depends on the specified activation function. So we're just going to call that f prime of x1. And so in general, for the derivative of the cost function with respect to some xi, we just have, it's the derivative of the corresponding y element times f prime of xi. And so our full vector is given like so. So this little guy here, that's an element-wise multiplication of the vectors rather than dot product. It's also called the Hadamard product if you are curious. Okay. So I'll briefly talk about two of the activation functions we're going to use. A very common one is called ReLU, which is given by this formula, the max of 0 and x. So all that looks like is when you pass in a negative value, you get 0, and when you pass in a positive value, you get a line with slope of 1. And the derivative here is pretty easy. It's 0 and 1. And then we're going to define one other activation function. This is called softmax. So y sub I is going to be given by e to the xi all over the sum of e to each x. And so what is this doing? Well, it's basically squeezing our entire output vector to values between 0 and 1 so that the total sum adds up to 1. And then these can be interpreted as probabilities. So if you think about like a classification problem, we are going to eventually compute some output such that the probability or the output of softmax corresponds to the probability that our input belongs to each class. And finding the derivative of this one takes a little while. So I'll just write it down and you guys can take my word for it. So given this matrix, right, where each y sub I is corresponds to our output. The gradient here, I'm just defining this as the matrix A, is given by A, the Hadamard product of the identity matrix minus A transposed dotted with the derivative with respect to y. Yeah, I'm going to put the source code for this neural network on GitHub. So if you guys want to see the precise derivation, I'll upload this to the same GitHub repository so you can take a look there. But for the sake of time, I know we all want to get into some coding. I'll move on. Okay. So last thing real quick, I keep talking about this cost function, but we need to actually define it, right? So there's a lot of different cost functions you can use, and some are better suited for different tasks. We're going to use probably the most common and most simple one in machine learning, which is mean squared error. And this is just defined as the average of the squared differences between our expected or desired output and our actual output. And using this, we want to find, okay, what's the derivative with respect to our output? Again, I'll save you the headache. It looks like this, where big Y without the star is our actual output and big Y star is our desired output. Okay, that describes the math. Sorry, that took a little bit longer than I wanted, but now we can do some coding, and I'm hoping that this won't take more than, say, 20 minutes. And are there any questions on the math we just did? Good. Okay, so I've talked about neural networks in the abstract sense, but we are going to solve an actual problem, right? So the National Institute for Standards and Technology, NIST, has this data repository of handwritten digits in 28 by 28 grayscale images. And each of those comes with a label. These digits are 0 through 9, and the label corresponds to what the handwritten digit is supposed to depict, right? So it could look like some 0, and then that's paired with a 0, obviously. And our goal is to try to predict the actual digit based on the image. Okay, so I'll start by importing some libraries. So we're going to use NumPy for the majority of our matrix operations. Can you guys see that? Good. Okay. And we're going to use matplotlib for some data visualization. We're going to use scikit-learn and pandas for initial data fetching and pre-processing. Yeah. Yeah. Good. Yeah. Cool. Okay. So using the fetch OpenML API from sklearn, we're going to get our data. Okay, so what is this doing here? Well, MNIST 784 specifies the ID of the data set that we're trying to fetch. As frame specifies that we want it as a pandas data frame. Return XY just returns it as a tuple. So we have our Y here, this is our target or our desired output, and X is going to be the actual data set, the images, right? And then parser equals auto. I just kept getting some warning from sklearn, and I threw that in and it stops giving me a warning. So, but that doesn't actually do anything. Okay, so we have this data set as a pandas data frame, but what we really want is a NumPy array. So you can go ahead and look at the structure of some of the data we just got. So for example, Y, this is showing the digits, and you can see the little quotations there. So this is actually as a character variable. So we're going to want to do some transformations here. We'll turn X into a NumPy array. And we're going to reshape it and normalize it. Okay, so these grayscale images are 28 by 28 matrices where each element is an integer from 0 to 255, indicating the darkness of the pixel in the matrix. And so I'm dividing by 255.0 here to convert it to a float and also normalize it to a number between 0 and 1. And I'm reshaping it here. 70,000 is the size of our data set. So I'm turning this pandas data frame into a NumPy array with 70,000 data instances. 784, this is turning our 2D matrices of 28 by 28 pixels into one 784 element vector, right? Because when we pass it into the neural network, we want a vector, not an array. And then going to turn Y into a NumPy array as well. And as I told you, it's currently stored as characters, so we're going to cast it as an int. Okay. And we can take a look at one of these images to see what we're working with. So voila, there is a grayscale image. Yeah, and remember we transformed these into 784 dimension vectors, so I just reshaped it there. Yeah. And remember, the first instance of Y was 5, so that makes sense. I think you've all got some pretty good neural networks in your brains, and we can classify that as a 5. Okay, so remember our softmax activation function. When we get our output, it's going to give us that vector Y from Y sub 1 to Y sub I, right? And they're all going to correspond to probabilities of the different digits from 0 to 9. But right now we have our Y stored as integers rather than arrays. So what we're going to do is a technique called one-hot encoding. So this essentially turns our like if we have some 3, it's going to turn into a binary classification here. I think that's the right amount of zeros, but the reason we want to do this is so that when we plug it into our cost function, we can measure the distance between the given output probabilities and the actual integer stored here in this one-hot encoded vector. Okay, so how are we going to do this? Well, we're going to create a matrix of zeros with dimensions y.size, right? That's how many instances of data we have. Yeah. And y.max plus 1. So y.max is 9, right? That's the largest digit we can have. And we want 0, 1. Yeah, there's 10 digits, right? So we want 9 plus 1. Okay. Unexpected indentation. Okay. Okay, and then doing the encoding for each variable. we're going to index this matrix using np.arange, which just creates a vector of integers, 1 to the specified variable, so y.size. So this is just going to call every single row of the matrix, and then we're going to pass in the variable. Yeah. Okay. Oh yeah, and we say that that's equal to 1, and that's our one hot encoder, right? Because y will specify the index of that array, and then we're going to return this. And then we transform our set of integers. Okay, now I'm going to split up our data set into a training set and a test set, right? Why are we doing this? Well, this is to protect from overfitting the model. If we have some model that only outputs, perhaps it can learn to output exactly what we tell it to every single time we train it. But what makes a model actually useful is if it can generalize to data that it's never seen before. So we reserve this test set that we're not going to show our model. We're not going to train our model on that. And then we can see what our accuracy is on the test set. Okay. So I'm going to take the last 5,000 data instances and make that our training set. And the first 5,000 is going to be our test set. And then I'm going to do the same for y. Okay, so that wraps up our initial data pre-processing. Now let's start building the neural network. Now remember when we talked about the implementation design earlier, we said that we were going to have each layer as its own standalone object. So I'm going to create a base class layer. And this will describe, well, our layers. And the input and output will be specified when we actually call the layer itself. And this is going to have subclasses which inherit these properties. So I'm going to define the forward propagation functions, but the specific forward propagation is going to depend on what type of layer we have. So when we create subclasses of this, that's when we actually tell our class what to do in terms of forward and backward propagation. Okay, so that wasn't too interesting, but now comes the fun part. We're going to create our dense layer, right? And this was the one that computed the linear combination of the input, right? So we're going to start with random parameters. So I'm initializing the weights matrix here and the biases vector. This should be rand n, by the way. Okay, and that's going to be our initialization for the layer. And then we can define our forward propagation algorithm. And this is just the dot product between the weights and the input plus the bias vector, right? This was our original matrix equation, y equals wx plus b. P dot dot. Okay. And then we need our backward propagation algorithm. So this is where we computed like the derivative of the cost function with respect to the weights, the biases, and the input. Okay, so remember the way to compute the derivative with respect to the weights was the matrix equation W times X transpose, right? And we want the derivative with respect to the gradient. And that was the weights matrix transpose times the input vector. The output gradient. Yeah, that was WT times partial C with respect to Y. Okay. Okay. And then remember the biases gradient, that was just the same as the output gradient. So we don't need to compute anything there. And now I didn't mention this before, but in gradient descent, the way to actually update our parameters given those derivatives that we computed is to just take what we had and subtract it by some learning rate parameter times the gradient we just computed, right? Because the gradient computes the direction of steepest ascent. So if we subtract that, we get the direction of steepest descent. And this helps us minimize our cost function to 0. And then our learning rate parameter, that just defines how fast or how much of a step or how big of a subtraction we want to take towards the minimum. Generally, a slower learning rate gives us a better minimum because there's going to be local minima and global minima. But yeah, Devin, any other question? Oh, thank you. Okay. We all good? Cool. Okay, so given what I just said, we're going to update our weights using this gradient information. It's just the learning rate times the weights gradient. And to update our biases, we subtract the learning rate times, remember the biases gradient is equal to the output gradient here. Okay. And then we want to pass back our input gradient. And that's going to go to the previous layer. Okay. That defines our dense layer. Now I'm going to build our activation layer. And this is going to inherit the layer base class. So we're going to need some activation function here and the derivative of that activation function. And we can set these. Okay. And now we want to define our forward propagation function. Pretty simple one here. We just declare our input and we pass through the activation function of our input. Okay, and then the backward propagation. This was where we had that Hadamard product between f prime of x and the derivative with respect to y. So np dot multiply does an element-wise multiplication here. And this is just computing f prime of the input, right? Okay, that's our activation layer. Now we want to specify our actual activation functions. Remember, we defined ReLU, which was the horizontal line for negative values, and the y equals x for positive values. So we can go ahead and create that. And you have to use np.maximum here instead of np.max, because np.max gives you the maximum value in the np array. Maximum computes an element-wise max between the two specified values. So it's just going to compute the maximum between 0 and x. Okay, and then our derivative is a pretty elegant way of doing this. Remember, it was 1 for positive values and 0 for negative values. So we're just going to return a Boolean here, x greater than 0. And so that'll be 0 if it's negative or equal to 0, and 1 otherwise. And then we are going to pass this up to the parent class. Okay, that's our ReLU function. We just need to specify our softmax layer, and then our cost function, and then train our network. Okay. See you, thanks. Okay. So when you're computing e to the very large input value, you sometimes get overflow errors here. So I'm just shifting, oops. I'm just shifting the element of each element of the input vector over to the left by the maximum. So when we raise it or raise e to that power, we don't get overflow errors. Okay, and then for our actual function, we compute it as e to the x over the sum of all the e to the x. And then we're going to return that. And then our backward propagation. Remember, this was that funky equation with the product or the Hadamard product of A times the identity minus A, where A is just the rows. The rows are just corresponding to each Y. So we're going to do this. We're going to do, let's see. And that was dotted with the output gradient. So on the inside, we have the identity matrix, minus that A matrix transposed times the A matrix. And that's dotted with the output gradient. I messed up some parentheses somewhere, I think. Here. Okay. All right, so that's our softmax function. Now, finally, we need to define our cost function, right? And so this is the mean squared error. So given some prediction and given some actual value, we're going to, it's the average of the squared differences. So this is np.power. Oops. Okay, that's our MSE. And then we also need the derivative of our cost function. And so that was 2 times the y star minus the big Y, if you remember. And our actual values here are listed as row vectors when we did the one-hot encoding. So we need to transpose those here. However, for some reason, when I did it like this, it didn't work. So instead, I did the equivalent by transposing the whole thing, right? So transpose is distributive. And so this is mathematically equivalent, but this worked and the other one didn't. I don't know, take it up with Python, not me. And then we divide by n. Okay, so those are all our important functions that we're going to use in building our network. So let's do that. Okay, so when we initialize our network, we're going to pass in a list of layers, right? And that describes our sequential model. And so when we forward propagate through our network, then we can just loop through these layers. Okay, so I'll define this predict function, and this is going to have two uses. So I'll initialize our output to equal our input, and then we're going to loop through the layers. And continuously update our output. And then we return our output. So this has two functions, right? This computes a prediction, but this also does the actual forward propagation for us. And now the fun part, going to define the training function. So in training our model, we're going to pass in some set of data, some x and y corresponding to each other. We're going to pass in our cost function, the derivative of our cost function, some validation split. I'll explain what that is in a little bit. Epochs, that's how many times we perform our forward propagation and our back propagation algorithm. We're going to need to define our learning rate. And I'm going to pass in one more parameter called verbose. When that's equal to true, then on each epoch, it gives us the status of the current epoch and the accuracy and things like that. Okay, so I'm going to create this dict, and that's going to keep track of our accuracy at each epoch and also our validation accuracy. So I defined this validation split variable. As our network's training, we're going to keep track of its progress by splitting the training set into stuff that the network is going to see and stuff that the network isn't going to see. And that's going to help us determine if our model is overfitting, because we're going to train it on the non-validation data and we're going to evaluate it on the validation data. Okay. And I'm going to get this size variable. That's just how many instances of data we have. Now I'm going to split our data, I'm going to get the size of our validation split. So this is going to be 0.2 times this size variable, right? Generally in machine learning, 80-20 is a pretty good validation split proportion. Some people do like 2/3 and 1/3. Some people do 50-50. It always depends. There's no good, always do this in machine learning. It always depends on your actual problem, but 80-20 is usually a good place to start. Okay, now I'm going to do the split. Okay. Now we are going to train. We're going to loop through our range of epochs and train it on each one. Okay. So I'm going to define these count variables. These will be helpful in determining our accuracy later. And now I'm going to loop through the training set. So for X, Y in. So we're going to do our forward pass, right? And that's where we use the predict function that we defined earlier, right? And so this is where we get our output. And now we need to evaluate that given our cost function and then do the back propagation. Okay, so this is our back propagation here. Right, so this is reversing our layers and we're going to loop through them backwards. And we're going to perform the back propagation algorithm for each layer. And then we need the gradient that it spits out, which is the gradient with respect to the input, which becomes that for our output. Okay. Now, in evaluating our accuracy, so this np.argmax just returns the element of the maximum value in our vector. So remember, we had all these probabilities in a vector, and we're just going to predict this as the maximum value in that vector. And we'll increment the count variable. That's going to tell us how many we got right. Okay, now I'm going to back out of this loop through the training set, and we're back in the loop of epochs. So we're going to compute train accuracy here. Well, that's just count divided by not size, but rather size minus split, right? Because we split it into the training set. And then we want to compute also validation accuracy. And to do this, we're going to loop through the, the validation set. And you might be wondering, okay, in the beginning, we split it up into a training set and a test set, and now we're splitting it up into a training set and a validation set. Well, the validation set on each epoch kind of gives us information about the progress of our model, right? So it tells us, like, along the way, if our validation is starting to diverge from our training accuracy, then that gives us information like, okay, maybe around epoch 15, we're starting to overfit the model. We reserve the test set for the very end. That's going to be data that it's never seen before. And then we can kind of evaluate our overall accuracy after training. Okay, so this is for our validation accuracy. And that's just going to be the proportion of how many we got right over the split size. And now, if we choose verbose, then we're going to print, then we're going to print our progress. So this is going to be epoch. right? So this is just saying like we're at epoch, say 1 out of 30. And this is going to tell us what our training and validation accuracy are. So this is just some print statement formatting. This is just saying like I want it as a percentage with 2 digits of precision. Okay. And we're going to do one more thing in this function, and that's to store these accuracies in that dictionary that we defined so long ago. And we're just going to return our history. Okay. Any questions there? That was a lot. The important part, the actual training of our network really just happened here. Everything else was so that we could keep track of our progress and our accuracy. Now, we're done building our network. Let's create one using the class we just wrote. So remember, we're going to pass in a list of, we're going to pass in a list of layers. So we'll start with a dense layer, which is going to take our 784 input variables. And here we've got some parameters. They're just kind of arbitrarily defined, but here we're going to pass that into 40 output variables. And then we need to apply our ReLU activation function. Then we're going to do one more dense layer. And we're going to map that to our 10 digits and then apply the softmax function. Okay. So in training neural networks, it's a lot of kind of tuning all these parameters. Like we had the learning rate, the number of epochs, and don't even get me started on the architecture here, right? You can have any number of layers and any number of neurons in each layer. You can specify any kind of cost function or any kind of activation function. But I was able to get pretty good accuracy with these parameters. So we're going to do 30 epochs and a learning rate of 0.03. Hopefully everything works. This is a good sign. It didn't throw me any errors yet. So this usually takes about 10 minutes to run. There's a lot of room for improvement in terms of optimization, but this gets you started with kind of the most basic network class. I'll spoil it for you. I ran it over here. This is the source code. Again, this is going to be up on GitHub. But so this is kind of what that verbose variable was doing. It's printing the training accuracy and validation accuracy on each epoch. So after 30 epochs, we were able to get to about 85% prediction accuracy, which is pretty good. Like I said, there's room for improvement. I mean, this takes 10 minutes to run. If you have a much larger architecture, say 4 layers, hundreds of neurons in each layer, then you're probably going to be able to get much better accuracy. But yeah, 85% is not bad. It's better than 10%, right? And so then you can write this function here to compute test accuracy. All I'm doing here is looping through the test set, same thing we did in the training function, and counting the number of predictions we get right and dividing by the total number of instances of data. And then here I'm just plotting the progress of the accuracy. One thing about gradient descent is you often get stuck on these training plateaus, and you can kind of see that here sometimes. Like, let's see. So here I was stuck around like 72, 73% for a couple epochs, and then I jumped all the way up to 80% in like 2 passes. And then I was stuck on 80%, 83% for a while. Maybe if I ran it for 50 epochs instead of 30, I would have jumped up again. Yeah, I think on one of the best runs of this, I was able to get up to about 90%. But yeah, and so here I have a little figure showing the actual test images, or the actual test images, and then the corresponding label that we predicted. So we're doing pretty well. Up there, we thought that 2 was a 9. So that's wrong. That's 2. Yeah, over there, we thought that 2 was a 3. I would give our neural network cut it some slack there. That's kind of like a curly 2. I might mistake that as a 3. Over here, that's actually a 7, but yeah, that's not bad. We got most of the images right. So yeah, that's all. That's the neural network.